Okay, so the fundamentals of chemistry really start at the atom. And so that's a great place to start with organic chemistry. And you may have probably surmised that organic chemistry really focuses on, well, this atom. But of course, you really can't have organic chemistry with just carbon. Um, that's certainly the central atom, but organic chemistry really doesn't get fun until you start incorporating nitrogen and oxygen and hydrogen. And you probably may have come to some early conclusion that organic chemistry is pretty ubiquitous. It's the chemistry of life. And so there must be something pretty special about this row of atoms and how they interact with nitrogen, oxygen, hydrogen, phosphorus, sulfur, and of course the biological salts that make us up, and that's a lot of sodium, potassium, magnesium, calcium, and chloride. So these atoms are pretty special in a pantheon of organic chemistry, and one of the reasons that they behave the way they do is their electronic configuration or their electronic structure and the valence electrons that they have that are associated with it, right? So we've really got to think back of, fundamentally what's an atom, right? And you know what an atom is. You can pretty well remember back to general chemistry that the atom is composed of a nucleus, which means the kernel of a nut, and it is made out of neutrons. Not always. Hydrogen doesn't have a neutron, but it's a popular element. And protons, which they all have to have a proton, and the proton has a positive charge, and the neutron has a negative charge. All right, and the neutron is utterly, or the nucleus is utterly tiny. It's femtometer 10 to the minus 15 meters. When an atom is about the size of an angstrom, so it's 10 to the 10 meters. So um, the nucleus makes up just such a tiny component of what we think of as the size of an atom. Mostly, when we think of like an atom or atom size, we include the electron, right? And the electron is going to be the most important part of organic chemistry. We're going to kind of treat the nucleus as a stationary spectator that um, hangs out and doesn't participate. It balances the charge of the electron, and that's unfair. Obviously, the nucleus is a very important component, but it's the electrons that really do a lot of the work. And so what I've drawn here is the atom deuterium. So that's an isotope of hydrogen. Normally, hydrogen does not have a neutron, but deuterium with its extra neutron does. You'll notice deuterium isn't up here on the periodic table because they don't really include isotopes of atom, but it's the same sort of electronic configuration as that, and you'd expect it to behave, and to some extent it does, exactly like hydrogen. There's just some minor differences in how it works. Now, as you start adding electrons, of course, you've got to balance them with protons, and then protons like to go along with neutrons, and you can add another electron here. And in the Bohr model, we have these sort of arranged in orbitals, so they they kind of exist in the same sort of sphere rotating around here, and this gives you helium. Okay, so now we're at helium, and you'll see in this periodic table I have, we've got the electrons associated out here as little dots, and those are the valence electrons. And to remind you what valence electrons are, you have to remember what the concentric shells, these things, in the Bohr model of an atom, right? So as basically Niels Bohr said, as you increase the number of nucleons, or the nuclear particles, protons, the shells will get larger, right? And then you get a couple more electrons out here, and more and more. And these were arranged into different atomic orbitals, right? And so in this periodic table, when I looked at these right here, these atoms, we called these the S shell. These would be in here, S shell. All right. And then the P shell, as you'll remember, would be out here. Okay, and everything is trying to become a noble gas, right? So a noble gas is noble because it's unreactive. And it's unreactive because starting with about carbon, or starting with carbon, every atom just wants to have 8 electrons in their outer valence shell. Once you hit 8 electrons in that outer valence shell, you really just somehow end up with this magical configuration where the electrons are and the protons just really are super content, right? Somehow that's just a perfectly balanced combination of nucleus and electrons, in such a way that these noble gases are not particularly reactive. Helium is almost completely inert. And, of course, at extreme conditions, you can get combinations of argon with other atoms. But in general, moving towards these 8 electron configuration, that's the goal, right? And so how then do the electrons end up stacking into these orbitals, right? So from the Bohr model, they sort of arrange themselves, or at least this is our picture of how they work. How they actually work is a bit more complicated. They're probability distributions of wave functions that exist around a nucleus. But in a simplified way that helps us think about the actual chemistry, we like to break them down into electronic configurations, okay? And those electronic configurations we put into s orbitals and p orbitals. And so when we talk about putting things into s orbitals, what I drew here is for helium. Let's go back here, get rid of this, get rid of that. This would be your first s orbital. So your first s orbital has 2 electrons in it. So that we would draw for helium. Very simple. All right. So what we write is we have just one s orbital. So that's your first period, one s. And then we draw an orbital, right? And then it's got 2 electrons. And we draw these 2 electrons as a hook. An electron, a single electron is always a little hook. And we draw them in opposing directions, right? Because if you think about it, how do 2 electrons hang out in the same cloud? Like, wouldn't they always be just opposed to each other? Like, that seems like a very high energy configuration to have 2 negatively charged subatomic particles coexisting. And essentially, what the idea of the Pauli exclusion principle tells us is that you can put 2 electrons and only 2 electrons into an orbital as long as their spins are opposing each other. Because remember, a charge that's spinning has a magnetic moment. And if it spins, say, clockwise, the magnetic moment will pay face. You can't see my hand, so this is a bit impractical. But if it spins clockwise, say, that magnetic moment will be up. And if it spins counterclockwise, that magnetic moment will be down. So in that way, you have a magnetic moment that, just like the poles of a magnet, they're opposites and they attract. So the south pole of a magnet likes the north pole of the magnet and they attract. And so that creates stability. And so that's sort of our rationalization of how 2 electrons can hang out in a single orbital. And in order to do that, we end up putting them in opposing electronic configurations like that, in different spin, if you will. Now, obviously, helium is pretty simple, but let's get on to something a bit more complex as a bit of a reminder, and let's look at carbon. Okay, so carbon is in the second row. So the first row, we still have to draw these in. These are the core valence electrons, right? So if we draw carbon, we still have a 1s orbital, and it's totally filled with the helium and these two. Now, if we draw the Bohr model, all right, so that is filled with the first one, and then the Bohr model, actually, let's go ahead and draw this down here. So, I'm going to erase this. I'm going to redraw it. I'm going to redraw how organic chemists think of it. All right, and organic chemists, like I said, we've kind of given up on the nucleus. We just call the nucleus the letter, all right, the letter C. If it were a nitrogen, it'd be the letter N. And now we can draw the electrons that sort of circulate them. And so the first s, of course, you've got an electron here. And that's your first s orbital in there, happy spinning around. Okay, and then your second s orbital, that's going to be your lithium and your beryllium down here. Now you got to go up to 2s, all right? And then 2s, of course, that's got 2 electrons associated with it. And that's your 2s orbital, all right? So 1s, that's your 2s. Okay, and now you're getting into your p orbitals. Okay, and so you've got essentially what you're going to have to call 3p orbitals, because we can pair these up. We can pair the boron and carbon, we can pair up nitrogen and oxygen, we can pair up fluorine and helium. And so this will just keep getting bigger. All right, and I'll make this a slightly different shade of blue. And then these, that's not nearly different enough. And that's too dark. Let's go ahead and do a different color completely for the p orbitals. What color are p orbitals? Let's say they're green. Now we got p orbitals, and we're going to start filling up the p orbitals around carbon, okay? And we said that there are 3 p orbitals around carbon because each orbital can only have 2 electrons. And so we've got, on our way to carbon, there's one in boron, and then there's one out here. Okay, so that's carbon. As it turns out, those orbitals don't have any electrons in them, so we don't need them, right? One, let's count them, okay? Let's go label that. And that is your, actually, as it turns out, your 1p orbital. Now I've done something a little wrong in this. I've told you there are other p orbitals, right? 2p, 3p. And I told you that spins, when you pair them up and they have diametrically opposed spins, they're happy. They're not that happy. You know, if an electron had to, it would rather be by itself. It doesn't want to be paired up. That's the lowest configuration after all. So what we're going to do is instead of pairing up that first one, we're going to separate them off into 2 different ones, all right? We're going to separate that one electron into the 1p orbital, and we're going to put that one here in the 2p orbital. Now they're 2 negatively charged electrons. They don't even have to worry about pairing up with spins. They are happy now. Now that third orbital doesn't have any electrons in it, so I truly can't get rid of that. Now how does this look? Now this now has a 1s orbital, all right? So that's your core. Now it's got a 2s, and I drew them in there. They're paired, all right? And now we get into the p orbitals, and the p orbitals, as you get out here, you'll remember, they are actually, so all these orbitals, I've drawn them out, but they've only got 1 electron each. They're pretty well at the same energy. If they've only got 1 electron, then they're going to have to be in the same energy. And we kind of make these distinction. We call the first one, and since I drew 3 of them, I keep erasing the other one. So I should probably just keep it, but it's empty, so that's why I keep erasing it. There's nothing in it. But we do have a bookkeeping obligation, so let's just keep it there, I guess. That's your 3p orbital. There's nothing in it, right? So whatever. But an electron presumably can shuffle around to any p orbital at once. And we put in a spin, all right? And we're not going to pair them up. That'd be too high energy. We're going to put this one here, all right? And so this is your 2p orbital. And your p orbitals, of course, to keep us all straight, they keep these. And you got to go review your Gen Chem textbook. This is really kind of a review. But we keep them straight by giving them sort of these x, y, not second x, z dimensions, right? And we fill them in. So what this says, as a picture, the 1s orbital is very stable, right? Because we can actually draw this. So this is relative energy. And what we can say is that the 1s orbital, that's very stable. That's all the way down here. Those electrons are not coming out. The 2s orbitals, they're still basically core electrons. They don't come out, all right? And then these 3 degenerate ones, all right, they follow Hund's rule, right? So let's keep track of some of these terms, right? Some of the words that I've been using. Pauli exclusion, all right? That gives us our pairing, Hund's rule. That says that we don't pair them up if there are other places for them to go just yet. Well, we'll pair them up when these 3 get full, but for now we're going to keep them apart before we start pairing, all right? And so there's our electronic configuration for carbon. Basically, what this says is it says we've got a place for 1, 2, 3, 4 more electrons on its way to become neon, all right? And in many senses, because these are such low energy, such stable electrons, we kind of ignore them. And you can see they're ignored up here in this table, which I didn't even make. They're ignored up here too, because those electrons truly do not contribute to the chemistry of what we're going to be talking about. And so what you see here are just the valence electrons. And those valence electrons are really going to be what's responsible for what we are going to be doing. All right? And so what is fundamentally important here is that we are going to be pairing up these electrons to create bonds, all right? And that moves us towards our more fundamental, what chemistry is all about, is actually putting something in these places to create a chemical bond, right? And so you can kind of imagine that these sorts of things really, when they pair up and they share an electron, they form something quite stable. Now let's just imagine something quite simple, okay? So we're going to do a very simple example. We're going to do Hmm. Hydrogen. Let's do hydrogen, right? That's silly simple. So hydrogen is just a 1s orbital and a 1s orbital. All right? We can draw hydrogen like I did up there. Hydrogen has an H, and it's only got one electron. All right? And so hydrogen atom, it's neutral, it's stable. It's not stable, actually. A single hydrogen atom wants to have a full, well, in this particular case, a full set of 2 electrons there. And so hydrogen wants to buddy up. So these 2 hydrogens, with their 1 electron, they want to form a molecule, right? And so that molecule is going to sort of combine these 2 orbitals, right? Because you're going to want to make a new molecule. So that's going to be like a hydrogen with its electron and a hydrogen with its electron, like that, all right? And so we're going to draw a line here, and that's going to make your hydrogen, dihydrogen. Hydrogen gas lights on fire, smells like nothing. It's pretty impressive. Blew up that dirigible, the Hindenburg, as we all remember that, right? So what happens when these 2 combine? All right, so you got to think, well, all right, so there's our 2 hydrogens. So what do they do when they combine? So there's this 1s orbital, and you can see the molecule here. I've drawn the molecule. Like, there's still 2 nuclei. All right, so we're not like eliminating these nuclei. They combine actually, and they combine to form sort of this new molecule orbital. We'll talk about that a little later. But one of these orbitals ends up going down, and it's good bookkeeping. You can't throw away orbitals. But what you can do is you've created a more stable molecule, right? So these 2 electrons actually end up lower energy, and they combine in a lower energy configuration. So that is your H2. And this is your energy, right? And if you remember from Gen Chem, things that are lower on energy are more stable. So this is great from hydrogen atoms perspective. 2 hydrogen atoms come together, they fill a full octet. That thing is more stable than it started out with. Of course, it still catches on fire, and it's like crazy. But as far as atoms are concerned, they are happy, and they form what's called a single bond. And we like to call single bonds sigma bonds for some reason, and that gives you your sigma orbital, right? And this guy up here, we're not going to really go too in depth right now. We'll get a little bit more. Sigma star, called an antibonding orbital, and that's, electrons, when 2 molecules react, this will become important. But right now, let's just talk about how to build a molecule on paper, how to pictorially build a molecule, because that's important, because we got to really learn how these sigma bonds are formed and what do they look like. Okay, so sigma bonds, if between carbon, because that's the interesting thing, right? We got carbon. Well, in fact, let's just do a molecule. All right, let's do carbon, 4 hydrogens. All right, methane. Now we're concerned with the valence electrons. We're going to keep this super simple. We're not going to do any sort of diagrams here. We're just going to look at these folks. We're going to learn how to draw before we learn how to do chemistry. We got 4 valence electrons right here. So we got to learn how to draw this first. All right, and so carbon with 4 electrons around it. Okay, and so what we're going to work on here, this sort of depiction where we draw the valence electrons to sort of illustrate how these sigma bonds are formed, they're called Lewis dot structures. All right, and now we got 4 hydrogens. I'm going to make the hydrogens red. All right, and hydrogens, we know, because we just did it, they only got 1 electron. And that means they can only form 1 bond, right? So that means our hydrogen has to go here. Now, if we didn't know they only had 1 bond, like we were still sort of in an 18th century modality, we could write all kinds of crazy formulations, right? If we thought, that could be an H, and that could be an H there, and that could be a C there, and that could be a H, right? But we're savvier than that. We know hydrogens form 1 bond, so this sort of stuff doesn't fly. And that's sort of how we can combine these letters together to start making some actual molecules. And so what I've got here is now I've got these 2 electrons paired up. And just like in this example of hydrogen, 2 paired electrons between 2 higher energy atoms that are otherwise missing electrons makes it for lower energy. So now these 2 electrons form a bond, these 2 electrons, and so on and so forth. So as you can gather, 2 electrons, these sigma bonds, they come together, right? That is a stable chemical bond. And in the parlance of organic chemistry, we call that a covalent bond because they share electrons. All right, those electrons are shared. So this white electron, that can orbit the hydrogen now because they're connected. They're part of a shared system. And this red electron from the hydrogen can now orbit the carbon. Okay, so these Lewis dot structures are kind of helpful. They sort of help you depict how to make a connected molecule. Now, let's get something a little bit more complicated. Okay, let's do C2H6. All right, that's a bit more complicated. Well, we know the carbons are going to be connected, so we just redraw the carbons. And hydrogen can only have one bond, but carbon can have four, so it makes the most sense to make the two carbons connected. And that's got four, right? And now we can add the hydrogens. Ooh, it's a little off, but that's okay. All right, now we can connect. Very good. That seems pretty nice. Let's do something with some crazy. Let's go above carbon, right? Let's look at nitrogen. So nitrogen, you'll notice, has 5 valence electrons. And so on this 2p thing, if it were nitrogen instead of carbon that I've drawn here, it would have now this electronic configuration. So that's the electronic configuration of nitrogen. So nitrogen now can make 1, 2, 3 bonds. All right, cool. Nitrogen makes 3 bonds. So if I draw this let's just say C1N, we'll say N1H5. It's because you still have what you've got over here. And so carbons are going to be white. Dot. Nitrogen, all right, nitrogen for some odd reason is always depicted as blue. So nitrogen's got 5 electrons. 1, 2, 3, 4. Let's put the 5th one on this. All right, 5. All right, then we populate with hydrogens. Hydrogen. And then I can put a hydrogen here and a hydrogen there. All righty. Now we got 1, 2, 3, 4. No. And something you're going to learn to love, a lone pair. So those 2 electrons are hanging out. Those 2 electrons just hanging out, that means business. This makes this molecule very reactive. Things with 2 lone pairs or just a single lone pair like nitrogen, those electrons are still perfectly capable of grabbing stuff. But this is a stable molecule. It doesn't need to grab anything. It's a neutral, stable molecule per valence shell. Doesn't mean it's unreactive. All right? Stable doesn't mean it's not going to react with anything. It just means it's neutral and it's quite happy. Now, drawing Lewis dot structures are going to be a little bit onerous, particularly as we get into things like let's just do C3H8, okay? Sure, we can draw this, and organic chemists are, you don't want to say lazy, but we like to pretend like we're efficient at least, even though that's probably just a code word for lazy. But there's no way we're going to be drawing that sort of stuff. I'm going to show you how we actually draw things as an organic chemist. It's going to blow your mind. You're going to love it, right? Ready? There you go. That's the exact same molecule. That's C3H8. Yes, I mean, literally, that's it. So if I wanted to do something that's like C4H10, I would draw 1, 2, 3, 4, right? So that's probably like pretty foreign to you, but if you look, what have I done? I've drawn that little, the end, CH3, CH2, CH3. This is like OChem shorthand, right? So the ends and the bends are carbons. CH3, CH2, CH2, CH2. So anytime I draw like a stick figure, I can draw this hexagon, and that's turns into a hexagon. These are just CH2s now. See how amazingly efficient that is. So I no longer have to draw dots, although that's super helpful. It paints a great picture of how bonding works. I no longer have to draw like letters. Now I can just straight up draw like a shape. So if I want to draw, methane you can't really get away from. You can't like draw a little dot, so you still got methane. Ethane, I guess I could just draw a stick, right? So that's CH2, CH2. But propane, right? So that's methane. Ethane. If I wanted to draw, say, ethanol, I draw my ethane, and then I would draw the OH coming off of it. Ta-da! And then that becomes ethanol. Okay, so these are fairly simple. All right, so in this lecture, what you probably picked up on is sort of a review of atomic structure and pictorial naming. Okay, so this is sort of our shorthand of how we're going to be drawing atoms or molecules. Molecules are composed of atoms that are bound together in discrete orbitals, and that is your first lecture.